Suppose I run into an integral like this. It's a product of two different functions. I think the first instinct a lot of students have is to just write it as a product of two integrals, but it absolutely doesn't work that way. So this would be the wrong way to do it. And this shouldn't be too surprising because the product rule for derivatives doesn't work in a simple way. So it shouldn't work this way backwards either. If I just took the derivative of my result here and thought that it would give me the product of the two derivatives, we know it doesn't work that way. The derivative of a product follows the product rule, so you have to go f prime g plus f g prime. So what we're doing here today is really trying to figure out what's the rule for the product rule working backwards. And the common notation for this is to use a u and a v and say I want to differentiate a product of two functions. Now, can I somehow take advantage of this to work backwards and find a solution to a problem like this? And so what I'm going to do is isolate uv prime. And then I'm going to integrate both sides with respect to x. And then I'm just going to clean things up a little bit. So v prime is dv dx. That leaves you with an integral of u dv. The second one's a little tricky. Right, the derivative of uv. And so what I have here is the integral of the derivative of a thing, or the antiderivative of the derivative. Those undo each other, and I just get a uv in the next line. And then the last one is du dx times v dx. In other words, the integral of v du. So we arrive at this formula that's called integration by parts. And really what we've done here is figured out how do we do the product rule backwards. So I wanted to look at actually solving an example. So you have to pick which one of these functions are you going to call u, and which one are you going to call dv, the differential of a function v. And the key to it is to pick a u that's going to get simpler when you differentiate it. So when I find du, it's going to be something simpler than it was before. And this gets simpler when I differentiate it. So I'm going to call x u. And then this whole chunk is the differential of a function dv. All right, so then I need to find du for the right-hand side of integration by parts, and that's just 1 dx. And then I need to find v. Well, I'll do this the long way once, but dv is sine x dx, which means dv dx is sine x. The derivative of v is the sine function. So in other words, to get v, I want to find the antiderivative of that piece. And that's negative cosine x. All right, so in the future, whatever my dv is, I just ignore the dx stuck onto it, and I find the antiderivative of the other piece to get v. So then let's plug in to integration by parts. I end up with uv, so that's x, and a negative cosine x, or negative x cosine x, minus the integral of v du, which is negative cosine x. I'll pull out the factor of negative 1, du, which is just dx. And then I have hopefully a simpler integral to do because I've wisely chosen which one would be u, and I've found a u that would make things simpler. Okay, so I've solved my first sort of product rule backwards kind of integral. And since it's the first one I've done, I'm going to check my answer. Let's differentiate this thing. It would be pretty remarkable to guess this. So it came from using integration by parts, but maybe if after you do enough of them, you'll start to guess some of them. So differentiate the first piece, and that gives me negative cosine x. I took the derivative of the first function, plus, I'll leave it as a minus for now, minus x times the derivative of cosine x, which is negative sine x. All right, now that's a plus. And then I have the derivative of sine x. All right, so I have negative cosine x, positive cosine x canceling out. It leaves me with x sine x, which is what I started with.